Hi everyone, welcome back. This is the introduction video for our lab 6. Um, so we're gonna do the Viterbi decoder on the FPGA in this lab. And so the first part of this menu introduced the encoding part. Okay, I guess has been introduced in a lecture, so I will skip it. This is a state machine. And yeah, this corresponding trellis structure used for decoding. Okay, we'll start from the decoding part. Okay, there are two submodules I want to introduce. These are going to be used in your design. These are the BMU and the PMU here. Okay, this is the lecture. The PMU is the unit of for calculating the branch metric here, the Hamming distance. This is to calculate the Hamming distance between the received parity bits and the expected parity bits. Okay, so in our design we will have 8 expected parity bits and 1 received parity bits. So in total you will have 8 Hamming distance as output. Okay, so let's look at the BMU design here. Let me see. Okay, we have the code. Code is um, R minus 1. By the way, the parameters here we use R and K. These parameters should be specified somewhere in the lecture. Here, right? The R is the number of the parity bits, and K is the number of the size of the sliding window here. Okay, so K3 and R is 2, same as the lecture. Okay, back to this BMU part. We have the code with the length of, what is the length? 2 here. Okay, this is the received code, length is 2, right? And we have this input is called state next. This is actually the 8 expected parity bits. Okay, so we will just calculate. Okay, the length of the state next is 16 here. So since each Hamming distance has a length of 2, so in total we will have 8 Hamming distance as output. Okay, the length of this is the same as the length of the distance out. Okay, the same length 16 here. We have a Lufan ruling here. This is to generate 8 Hamming distance submodules to calculate those branch metrics. I have added some more comments here. I will update this version of the code later. So if you previously download the code before this time, 9:40, you can download the updated version with more comments. Okay, so I have listed here how this part is connected. Okay, so we just calculate the Hamming distance between the code and each 2-bit chunk of this state next, and output this Hamming distance to the distance out. W is a wire here. Okay, we have wires, and here we have the wires connected to the output ports. This is just the Hamming distance submodule. I will not go over the details of this. Okay, just calculating the Hamming distance. And this is a Hamming branch metric here. So on the left in this picture, the illustration is the input, the code is these two, and the distance out should be these 8 red numbers here. Okay, as you can see, the maximum Hamming distance should be 2, since we only have 2 bits, right? So So 2 bits denoting the Hamming distance should be enough. And we use 1 1 denoting the infinite distance. We will talk about it later. Okay. And then we will introduce the PMU submodule here. So PMU is like this. So for the PMU is the unit calculating the path metric. Path metric is a cumulative branch metric. Okay. Okay, that corresponds to the path in trellis with a minimum Hamming distance, right? This is actually the cumulative minimum branch metric. So, for example, we have a path here, and yeah. So, for example, we have a path from 0 to 2 to 3, and it stops. So here, the path metric, each state, each square box here have a path metric. It corresponds to the minimum cumulative Hamming distance from the first column here. Okay. How do we calculate the path metric? So we have this equation. So for each box, as you can see, for example here, for each box we have 2 possible inputs. And we choose the minimum, we choose the path with the minimum possible cumulative errors. For example, for this box, we can have the path here, the cumulative distance is 0 plus 2 here, it's 2. And the second possible input here is the error is the infinity plus 1 is still infinity. So we choose the smaller one. Of course, the smaller one should be the first. So the path metric corresponding to this box is just 2. Okay. Let's look at the actual design. We have the input and the distance path output as path output and distance output. Okay, so each PMU module corresponds to 1 column or 2 column in this trellis structure. Okay, and this distance input is let me see what it is. Okay, this is a path metric on the previous column here. So in total, what is the length of this? Okay, it should be 32, I guess, here. So in the PMU, we use 8-bit to represent the path metric. And here we have 4 path metrics. So 4 times 8, this should give us 32 as a length here. Okay. So this distance corresponds to these 4 previous path metric. And distance path, this is the 8 Hamming distance we have. And so where are the 8 Hamming distance? These are the Hamming distance, these 8 2-bit numbers, right? These are just the output of our BMU here. Okay, we have 8 Hamming distance on each edge, on each edge here. And we just calculate the summation of the path matrix and the branch metric on each edge and pick out the minimum one for each of the state on the second column here. Okay, and we will output this path metric into this distance out. Okay, distance out should also have 32 bits, and we will also save save the path where it comes from in this path out signal output. So for example, we want to know this is true, right? This path matrix is true, but we also want to know which edge it comes from. So we will also record this information in this path out signal. And still we have, so the core of this part is just the comparing of this summation, right? So we have this compare submodule to do this job. Let's look at the definition. So for the compare, basically it's just this equation. Okay, we have two possible inputs edge for each box, right? So we have 0, distance 0, and path 0. This is the path metric, and the branch matrix corresponds to the first input. And we have distance 1 and path 1. This denotes the second possible input for this box. Okay, so we just take the summation of this. Let me see where it is. Okay, we take the summation of this distance plus path, okay, for the distance out 0 and distance out 1. And here you will notice this infinity. Okay, so sometimes we have infinity distance here. How we're gonna represent infinity with a limited number of bits? We just there's a convention. We just used all ones to denote infinity here. Okay, since we have 8-bit for the distance, so when we convert it into the hexadecimal representation, we have FF here. Okay, so here we just pick the smaller one. So if 0 is smaller than 1, the final distance output will come from 0. Otherwise, it comes from 1. And also we also save where it comes from. Okay, so this is a 1-bit output for the path out. Right? It's either going to be 0 or 1, right? Okay, let's come back to this PMU module. So we have in total we have 1, 2, 3, 4. We have 4 compare submodule connecting these signals. This is kind of complicated. These are kind of hard to understand, but I have already showed the details in these comments. You want to know why it is connected like this, right? Okay, so these numbers basically corresponds to this trellis structure. This is critical. Okay, please understand why it is connecting like this. Okay, and also I will talk more about the output. The distance out should be easy to understand. These are just the path metric on the next level here. But the path out is critical. Okay, so we have in total we have 4 path out. Corresponds to 4 states. Each state is 1 row here. Okay, and each of these path out actually contains 3 bits. Let's see the length of this path out. Here, this is 2 to the power of, what is this? Sorry. This is the length of 12. This should be 4 times 3. Okay. 4 is 4 boxes, and 3 each of these we have 3 bucks. So output is illustrated here, but you want to understand this. Okay. The top 2 bits of this, each of the 3 bits are fixed. They are 0, 0, 0, 1, 1, 0, and 1, 1. They correspond to these 4 state bits here. Okay. And the last one is the path selection bit. Path selection bit is just the output of this compare path out. Okay. Another meaning of these is remember that. Let me see. Yeah. So for the state here, this is actually the xn minus 1 and xn minus 2, and this path selection, it is actually, I think this should be xn. So these 3 bits actually, actually, so when you combine them together, they are actually xn, xn minus 1, and xn minus 2 here. Okay. This will be used later when you do the decoding. Please make sure you understand these 2 comments. Okay, these are critical when you do the decoding. Okay, I think I have finished the introduction of these 2 submodules. And let's go to this Viterbi. Oh, by the way, this PMU and BMU are already written for you, so just make sure you understand them. And what you're gonna do is write your code on this Viterbi module. So some of the part are already written for you, except for the always block. I will not scroll down. Okay, let's just look at the first half of this. So we have instantiate 1 BMU and 1 PMU for you, and we also have some signal connected as an input and the output. Of course, if these signals doesn't make sense to you, and you can also create your own signals and replace it here. Okay. This is just a suggestion, but not a restriction. So what you're gonna do is let me see. So where is let me see. This is a lecture, right? Okay. So what you're gonna do is you will have the input of the code in. Code in is a code word you're gonna receive. Let's look at the test bench provided. Okay, these are the code word in the test bench, but also you can change to anything else to fit in your own case. So for example, the code word is just like this. Okay, 1 1 1 0 1 1. Of course, they are different. So this is different from the lecture. Let me see if I have the same one. Okay, this is the slide from last year. Okay, these are the same in the test bench. We have 1 1 1 1 0 1. Let me see. Okay, here we have 1 1 1 1 0 1 0 0 0 1. These are the first 5 input. Okay, so in this slide there are 6, but in the test bench there are only 5 here. And state is also the input for your module. Okay, states here. These are actually, let me see. I think these are the output of the state machine, remember that this state machine is generated from this encoding part. And a successful Viterbi module should be able to decode not only this encoding machine, but also some other encoding machine. Since the encoding machine only depending on how you generate this parity bits, right? So this output of this state machine is also the input. For example, you will have 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 0. These are the input of this module. Should be the same here, right? But in the reversed order, I think. Yeah, they're the same. Anyway, you can keep this. For this part, you can temporarily forget about this and only modify this part. Okay, in your simulation. So when you do the when you build this module, you wanna check. You will iteratively fit in every 2 bits of this code into the BMU first. Okay, so for example, where are the BMU slides? Oh, here. Sorry. You will first fit. For example, you will first fit into the top 2 bits of this part into the BMU, and once you fit it into the BMU, you wait maybe one cycle, and then you will have 8 Hamming distance here, and you feed these 8 Hamming distance into the PMU. Let me see. Distance states should be the distance passed out, right? As you can see, the distance passed out should be the Hamming distance output, right? And then it's automatically fit into the PMU module here as a distance path here. Okay, right, and also this distance 0. This will be initialized as like this. Okay, so since we assume we always start from this 0, 0 state, so the distance is gonna be initialized as one distance is 0, 0, and the rest of the distance are all infinity. Okay, what you're gonna do is iteratively feed 2 bits of this code in to the BMU and then to the PMU, and you will save the output of the PMU to somewhere you prefer until you run out, you reach the last column of this structure. This is when you run out of all 10 bits of this code in, and finally you will pick the minimum distance from the last column, and that would be our path selected. So personally, I have write this by myself, and also I encourage you to do the same for yourself. Okay, so this is the case for our test bench I illustrated here. Okay, we start from 0 and 3 infinities, and then we keep populating to the next column, until we reach the last one. So in this case, we are very lucky. We have one path matrix equals 0. Okay, this is a minimum one, and this minimum one, and here I saved the output of the path metric in each column here. Okay, and also the distance. As you can see, the distance 2, infinity, 0, infinity. These corresponds to these numbers. Okay, and we will start from this very last one with the minimum path metric. This is corresponds to state 0, 1, right? And this is just this underscored 3-bit here. Okay, and we will backtracking. So we want to know what is the previous state of this state. We just look at the lower 2 bit of these 3 bits. Okay, the lower 2 bit is 1, 1. Okay, which means this is corresponds to this 1, 1, and we jump to this box. This is a parent box of this box. Okay, and for this one, let me see. Since this is the third state, right? So this means that we will look at this underscored 3 bits of the path metric output. And how are we gonna know what is a previous box? What is a previous state? We just look at the lower 2 bit. Okay, it's 1, 0, and we jump to the 1, 0 state. On the previous column, we go to this. Okay, and so on. We will go to here, here, and finally here, and we will backtracking the state. And how are we gonna know? How are we gonna do the decoding? We just look at the top 1 bit of each of these 3 bit. Okay, so here we have 0, 1, 1, 0, 1. These are just decoded output here. I just tell you how to extract this information, but I think you should understand why it is a case like this. Okay, I also have these here. This is the same thing I just told you before. So okay, I guess this is it. You will just first part, you do the forwarding, and then after you reach the last column, you do the backtracking, and finally you will have your decoded code output to the code out, and also you have finish set to 1. Okay, and let's see. This is my simulation, but it's highly likely you will have different ones because maybe we have different interpretation how these internal signals. Let me show you how to do this. So one way to debug is in this simulation you actually select scope and you click on your Viterbi and you select the signal you are interested in. You right click it and click on add to wave window. Okay, so in this way you should be able to see the internal signals in your design in the simulation. Okay, so after you adding them, you click on this relaunch the simulation. You will just be able to see the internal signals here. Okay, so one way to debug is to strictly check what are the output of your BMU and the PMU and how you save them into some registers or wires, and really check them, make sure you have the right signals. Okay, I guess this would be it, and good luck on your design. Yeah, thank you.